Hello everyone and welcome to QuantPy. We are going to derive the Fokker Planck equation for some important processes. This equation is also known as the Kolmogorov Forward equation. For the context, there are two popular ways to derive the Fokker Planck equation. One is through the master equation, which is very similar to the particles approach we adopted in the previous video and a topic for another day. And the second approach is through the SDE, which uses combinations of Ito's lemma and expectation. This is the approach we are going to take. We will start with the Brownian motion, which will give us the diffusion equation we saw before. So the Ornstein diffusion equation is the Fokker Planck equation for the standard Brownian motion. And we will then move to a general SDE, where we will assume that the drift and volatility are functions of time and the stochastic process. This will give us the Fokker Planck equation for the general SDE. We will then apply the solution to geometric Brownian motion and the Ornstein Uhlenbeck processes. We will then explain some terminology such as the infinitesimal generator and semigroup. So in a short video, we are going to cover a lot. To motivate the SDE approach to the derivation of the Fokker Planck, let's quickly outline how the Ornstein ensemble of Brownian particles view is linked with the Wiener's mathematical model of the Brownian motion. Einstein applied statistical treatment to a large collection of particles to deduce the mathematical properties of the Brownian motion. You can view the Wiener's definition of Brownian motion as applying the probabilities computed on the ensemble to the trajectory of a single particle. So roughly speaking, you can say Einstein modeled and calibrated the probabilities of the Brownian particles on a large sample, and Wiener then applied this model to a single particle. We know the Wiener process. It starts at 0 and has independent increments, which are normally distributed with mean equal to 0 and variance equal to the length of the interval. You just have to take the Einstein solution and plug 1 divided by 2 for the d to get this probability density. And once you have this mathematical model of the Brownian motion, then it's not hard to write the SDE. Just for the sake of generalization, we define a process x as equal to b, so the SDE is just dx equals db. Now we are ready to derive the Fokker Planck based on this SDE. First, let's say we have a smooth function of x. This is just an arbitrary function we introduce so that we can apply Ito's lemma. Because this function is arbitrary, we will get rid of it later. We assume that this function is twice continuously differentiable and has compact support, which means it vanishes outside its support. What it means is that there exist x1 and x2, so that the function gives 0 outside this interval. We assume that its derivative also has this compact support. When you think of this function, think of the probability density, not the option price, and it will make sense. We can calculate the differential of this function by applying Ito's lemma, which is first derivative times dx plus half the second derivative times dx squared. Dx squared is easy to calculate. It is just dt. Now we can plug in the dx and dx squared into the Ito's lemma to get. Now to remove the stochastic term, let's take expectation of both sides. The expected value of the function with respect to the Brownian is equal to 0, so the stochastic term disappears. So the randomness has been removed from the stochastic differential and taken into the expectation operator. You know expectation means integral with respect to probability, so this is a step forward. Because remember, Fokker Planck equation contains probability density and place of the Brownian, so you can see we are heading in the right direction. Now we can take the dt to the left hand side and interchange the expectation and the differential to get. By the way, this can be justified by invoking one of the convergence theorems, the dominated or bounded convergence theorem. Now we can write the expectation as integral with respect to the probability distribution of x. Let's represent the probability density of x at time t by p. So we can write the expectation as follows. Now we simplify the right hand side. Essentially, we have got the second derivative of f with respect to x, and we want to get rid of the derivative of f. Easy to do, we just need the integration by parts formula. For our integral, we obviously call the derivative term as the dv part and the other term as u. So integrating dv, we get v on the left hand side, and the derivative reduces by 1 on the right hand side, and differentiating u we get. So we are ready to plug these into the integration by parts formula. By the way, remember f is just a facilitator. Our main target is p, because Fokker Planck equation describes the dynamics of probability density. So in the end, everything will be in terms of p. So this is the direction of travel. Now we know the probability tails up really quickly, and the function f vanishes at both ends. So f times p will be 0 at both infinity and minus infinity, and the first term is 0. Now we need to apply the same integration by parts once more to get f on the right hand side. Currently we have its derivative with respect to x. We know the drill now. We define the derivative of f as dv, and the term containing the probability as u. We then integrate dv to get, and calculate the differential of u, and we get the second derivative of the probability. So the integral becomes, where we just use the integration by parts formula again. Now the first term is again 0 for the same reasons, so we get. Now we take the derivative inside the integral. Now we shift the terms to the left hand side, combine the integrands and factor out f. Now remember, f is arbitrary, so if this integral has to equal 0 for arbitrary function, it means the terms inside the brackets must be 0. And this is the Fokker Planck equation for the standard Brownian motion, which is essentially the diffusion equation that we are familiar with. Now let's complicate the SDE a bit. Let's try a more general SDE, in which the drift and the diffusion terms depends on the value of the process. So in comparison to the Brownian, we now got a drift and diffusion, and they are not constant, but the derivation is going to be as easy as before. Plus, we know what to do now. We take an arbitrary function which has compact support and is twice continuously differentiable, and apply Ito's lemma to this function of x. We substitute the SDE and dx squared into the Ito's lemma to get. We will drop the dependence on x and t, but they're always there implicitly. Now we combine the dt terms. Now we take expected value of both sides. So we are talking averages now, which has removed the stochastic term, and the randomness has gone into the expectation operator in the form of probability density. Next, we interchange the differential and the integral and shift the dt to the left-hand side. Remember the explanation for this? Now let's represent the probability of x to equal small x at time t by p. And remember, this p is the main object of interest now. So we can write the expectation as integral with respect to the probability, where now is probably better to write the mu and sigma as explicit functions of x and t, as x is now the integration variable. Now we can write the integral of the sum as the sum of the integrals, so we get. And now we have two terms on the right hand side, so we will apply the integration by parts to each of them separately. We will start with the first term on the right hand side. So for the integration by parts, we will set dv equal to the derivative of f, and the other two terms are then the u. We integrate dv to get v, and differentiate u to get du. Now we are ready to plug these into the integration by parts identity. So we get, now as before, the first term is 0 because the function f has compact support and the probability tails up. By the way, even if we don't know the mathematical formula for the probability, we can justify this based on the physics. The probability of a particle traveling infinite distance in a small amount of time is going to be 0. So we can replace the first integral. Now for the second integral, we have the second derivative, so we will need to apply the procedure twice. So we take the derivative as dv and the remaining term as u. We integrate dv to get v, and the derivative on the right hand side reduces by 1. We differentiate u to get du, and then plug these into the integration by parts equation. So the first term is again going to be 0, so we are left with the second term. We can apply the integration by parts once more to get rid of the derivative of f. We know what the procedure will produce, so I'll just write the end result. Essentially, the derivative of f reduces by 1 and the derivative of the remaining expression increases by 1, so we get. Now on the left hand side, we interchange the derivative and the integral to get. Now we combine the integrals. Now as f is arbitrary, it means the terms in the brackets must be equal to 0. And this is the Fokker Planck equation for the general SDE. Now to see the rewards of the general derivation, let's see how easy it is to derive the Fokker Planck for some common SDE. We saw earlier that if x is the standard Brownian motion, then the Fokker Planck equation is as follows. You can derive this easily by substituting 0 for mu and 1 for sigma in the general Fokker Planck equation. Now let's say we have the Ornstein Uhlenbeck process SDE. So this is the same as the Vazicek model, but the long-term mean is 0. We just substitute constant sigma for sigma and kappa times x for mu into the Fokker Planck equation, and taking the constants out of the derivative, we get the Fokker Planck equation for the Ornstein Uhlenbeck process. Finally, let's see the famous geometric Brownian SDE. So the function mu equals mu times x, and the function sigma equals sigma times x, so we get. And taking the constants out of the derivative, and we get the Fokker Planck equation for the geometric Brownian motion. Now let's quickly discuss some terminology that comes with the Fokker Planck, particularly in the discussion of the Markov processes. Let's remove the dependence on time because it can complicate things when it comes to Markov processes. Now we can write the Fokker Planck and the differential operator form. So essentially, we can write the finite approximation of the derivative on the left hand side and represent the differential operator by L to get, where L is given by this expression. This is known as the infinitesimal generator. Remember, infinitesimal really means infinitely small, and generator is the concept used in the Markov chains, etc. The infinitesimal is, roughly speaking, the same thing as the Taylor series local approximation. So you can see the parallels now between the infinitesimal generator and the Taylor series. Also, remember the Black-Scholes delta hedging? They were also kind of using the infinitesimal approach to replicate the option, right? Now for a Markov process, this essentially gives the change in probability over a small interval. And as you would remember, you can construct the Markov process from transition probabilities. So this infinitesimal generator is an alternative way of describing the Markov process, but this approach is more general. Reason being, for the processes we discuss, such as the Brownian or the Ornstein Uhlenbeck, it's easy to get the transition probabilities, but these are exceptions, and for many processes, the transition probabilities are not known in explicit form, so this infinitesimal generator enables us to construct many more processes than would be possible with the transition densities. And as we have been seeing throughout this playlist, when you solve this infinitesimal generator for the processes we have been discussing, you get the explicit expression for the transition density as you would expect. And if you don't like the word infinitesimal, then you might as well call it local. Now, for another interpretation, if you rearrange the equation, you will see that it's in the same differential form as the continuity equation, which is a stronger form of the conservation laws. For example, the law of conservation of energy states that the total energy in the universe is conserved or fixed. That's sensible, but the law will still be satisfied if you were to remove some amount of energy from the Earth and create the same amount of energy on the Mars instantaneously. But you know this is not true. So the continuity equations are stronger form in that it precludes this teleporting by requiring this flow must be continuous. And the continuity equation just captured this mathematically. And as we said, this is a stronger local form of the conservation law. So again, we see the infinitesimal form models the local behavior. Another technical term that you would hear in this context is the semigroup. Sounds abstract and dry, but you know a group is a mathematical structure. Just imagine a set of elements with some boundary operations which satisfy some properties such as the familiar identity, invertibility, associativity, and closure. The invertibility creates problem in the present context, so the semigroup structure is used, which has fewer restrictions. It essentially has just one property. Think associative property of multiplication. And to make this semigroup concept work for the changes in probabilities, you impose some regularity conditions such as identity and continuity, and you get a very general unified theory of Markov processes. Big words, but it's rather very simple. The key to this semigroup property is the Chapman-Kolmogorov equation for Markov processes. You know this equation just says that the probability of going from x at time t1 to z at time t3 is equal to the probability of going from x to z through an intermediate point integrated over the range of such points. For time homogeneous processes, the transition probability only depends on the length of the interval and not the time, so this simplifies. Essentially, you can assume the starting point is 0 and then just focus on the length of the interval over which you want to calculate the change in probability. Conventionally, the 0 is dropped because it adds nothing. And let's represent the length of the interval from t1 to t2 by s and the length of the interval from t2 to t3 by t. So the length of the interval from t1 to t3 is then equal to the sum of these two intervals, which is t plus s. Now, motivated by this form of transition density, we can define a one-parameter operator. So this is more or less the conditional expectation given the current value of the process. We should write the operator more formally as being applied to function f at value x, but this kind of takes too much space, so we will just represent it with the p underscore t, but we will keep the formal definition inside. Now, how does the semigroup come about? We can write the same operator for the total interval t plus s as follows. Now we substitute for the conditional probability from the equation at the top. Now we can rearrange the inner integral. The aim is to split the transform, and you can see we have achieved that as the inner integral is now the operator, or p underscore t. And now this whole expression is like the transform of pt, so we can write it as composition of the transform, which is the s transform of the t transform. And if we remove the circle, which represents the composition, then you see you got the semigroup associative property. So our transform is a semigroup, It's easy to check that if you substitute 0 for the parameter, you get the identity. And we just need to add one more assumption that this transform is continuous. And if we do that, then it's very easy to express this in terms of the infinitesimal generator. Let's see. You can calculate the rate of change of probability using this operator P as follows. And then using the semigroup property, we can factor out P. Now, the left-hand side is just the derivative, and representing the limit on the right-hand side by A, we get the Fokker Planck equation. And as we said before, this is also called the Kolmogorov Forward equation. And if we assume that A is not a function of t, then we know the solution of this equation is just the exponential of A times t. And this A is the infinitesimal generator. This relationship between the semigroup operator and the infinitesimal generator has been well studied. You can start by looking up the Helly-Uceda theorem, and we will come back to this topic when we derive the Fokker-Planck through the master equation. I hope you enjoyed the derivation and the explanation, and I look forward to seeing you in the next.